Humanoid soccer requires agile locomotion, dynamic object interaction, and strategic gameplay. In this work, our contribution is to show how deep reinforcement learning can produce high-quality individual skills like kicking, running, and turning, and to sequence those skills fluidly into agile reactive policies which work robustly both in simulation and on the real robot. We use the Robotis OP3 robot platform, an affordable miniature humanoid with 20 controllable joints. We use the basic onboard sensors, joint positions, accelerometer and gyroscope, and learn a policy that issues target joint angles using only the onboard computer. The policies shown here additionally use a real-time motion capture system to observe the locations of the two robots and the ball. We then defined a simplified 1 versus 1 soccer game, with two opponents playing each other in a 5 by 4 metre fixed-sized court. The agents are rewarded for scoring goals and penalised for approaching closer than 1 metre toward the other robot. We trained these agents entirely in simulation, using a few stages of training with an off-policy reinforcement learning algorithm, distributional MPO. We first trained two teacher policies, one that can get up from the floor and one that scores goals starting from an upright position. Then we distilled these two teachers together into a single student policy, using KL regularization towards both of the teachers. This regularization was annealed away during training, leaving the final behaviour free to optimize the task reward. Finally, the strategic skills of the resulting policy were further improved by several rounds of self-play. Training in simulation was important to enable us to reach the millions of episodes needed for agile gameplay. However, we also had to ensure that the learned policies could be robustly and safely transferred to the real robot. This was challenging for such dynamic policies, especially with a fairly low-cost and low-precision platform. In order to promote robustness, we added noise during training and simulation, such as random pushes, observation noise, and perturbations to the simulation dynamics model. We also took care to add delay to the simulation, while minimizing latencies in the control software of the real robot. These randomizations, together with a control rate of at least 40 Hz, enabled stable zero-shot transfer. The robots are susceptible to damage of the gears, especially in the knees, from the transient shocks that occur during dynamic kicking and stepping motions. To reduce the risk of breaking the robots during gameplay, we penalised high torques in the knee joints in simulation, and this successfully encouraged the agents to learn softer gaits. Finally, we can examine the resulting policies on the real robot. Comparing the individual skills to the open-loop built-in motions provided by the manufacturer, we see that the learned policies are more than twice as fast at getting up and at walking. However, the real improvement in agility comes from the seamless integration of these skills into a single policy. The learned policy naturally rejects disturbances and recovers from falls. It can also turn quickly and position itself to shoot accurately at the goal, even intercepting moving balls to do so. It also exhibits higher-level strategic behaviours, such as positioning itself to defensively block the opponent's shots. Please see our accompanying paper and website for full details of the work.